So today we will start virtual memory, and this is a topic that we had covered in computer organization, and now we will be covering this again in the operating systems because one, it's so important, and second, the virtual memory system is actually a good it lies at the intersection of hardware and operating system working together to provide a really useful service for the programmers. A lot of the slides that I have discussed here will just be a reminder for computer organization. Let's just discuss this. So first, the idea is between memory management, we want to provide a real abstract view of memory to the actual user. What we mean by this is with the programming, you should really not care about how much physical memory you have. So it is your physical memory and you have no idea how much physical memory you have and how many other processors are actually being executed in the physical memory and all other things. So you just like from your application program point of view, you just malloc as you wish. You declare your data structures as you wish. You can recurse as you wish, and you just don't worry about the physical memory that you have underneath. That's the first thing. The second thing is provide isolation between different processes, meaning that you will have like in our physical memory, this is say the memory that's located for allocated for P1, and here's another one for P2 and P1 and P2. Basically, despite the fact that they are neighbors in the physical memory, we should still provide isolation between them, and this is mainly for security. I really don't want you to access my memory when I'm editing the midterm files on the same machine. And third is we want the physical memory is usually very little compared to what's provided in the virtual memory system. And what you want to do is you want to only bring in most essential parts of the code and all the other things into the physical memory. Okay, and this is important. We have seen in computer organization that you have up to I think how much 2 to the power 47, so basically 48 bytes of virtual memory, which is way more than that you have on the physical system, and you won't use it, but it's really good to feel that if you wish, that kind of world can be created as an illusion to this. And finally, whatever we do, we want to make sure that the overhead of implementing such a memory management system should be minimal. And towards this, we have studied that how we can translate virtual addresses into physical addresses. So this is the main issue that the CPU essentially works in the virtual address space, which is not true. Okay, and we need to map this into physical, basically addresses. Okay, and this is where the matrix actually metaphor comes in. In a sense, your CPU is living in the matrix because from the CPU point of view, it thinks it has so much the process that's running on the CPU. It thinks that it has so much address space, whereas in reality, it has much less. And this illusion from virtual address space to physical address, because this is what the memory management unit does. And in doing this, we have seen that this has happened. This is usually implemented with paging and TLBs, and there's this page table management. So all these things we have discussed in 331. Okay, and I will remind you what those were. Now, in all these things, we said that we have learned about page faults and etc. And a lot of the time, if you think in the physical this is my physical memory. The idea is, whenever you, like from your virtual memory, you bring in and allocate new, basically, pages from the virtual address space, which is nice. But when the memory becomes full, then we need to start replacing pages with others that's incoming. So that means that we have to kick out some of the pages. And that part we haven't discussed in computer organization. This is the part, this is the new part in 334, and this is especially the page replacement policies. And you can see that like we have this, this is policy, and then we have the mechanism. If you remember, we have discussed this in the case of scheduling, where the mechanism was the context switching mechanism. There's only one way to do this, but then there were policies, and policies means that there is no single policy that will make everybody happy, and some policies make some sort of processes happy, and etc. etc. We have discussed this, and we will do the same thing with the page replacement policies. Okay. And, so basically, it's an abstraction. The version memory is one of the main abstractions for the process, and it means that your program can run on machine with less physical RAM. Okay, and the main observation was that the many programs don't use all of their code or data. This means that in this case, this is my virtual address space. Okay, which is in the 64-bit system. It's 48 bytes, which is huge. Okay, and in reality, you will be basically using only a little part of this. Okay, maybe a little bit of here and a little bit of here. Okay, and there's this waste spaces that are actually not being used. Okay, and most and almost all programs, okay, like you never use this, but it's good that you have this ability. Okay, and it's because, like, for example, I'm running my PowerPoint right now, and my computer is never connected to the printer, so that means that the code that's related to printing in the executable should be on the disk, and it should remain on the disk. There is no point in reading that one in and bring it into the physical memory. And this is why the version memory does this. And so the operating system looks at the runtime behavior of your process, and based on this, then it allocates memory, physical memory, based on its taste and based on which basically options are selected, etc. The second one is, as you said, the version memory isolates processes from each other, and this is, as I said, the one process cannot access the memory of others, and this is actually the basis of protection between different users sharing the very same machine. Okay, and this virtual memory, it basically has hardware and operating system support. So this part was 331, and this is where we are discussing in 334. Okay, and the hardware support was, the memory management unit, TLB, which is transaction look-aside buffer, and the operating system buffer was how to control the MMU and TLB, and etc. So, okay, so we will be discussing, what the memory management requirements are. So we have this, we will discuss a number of different mechanisms to implement this, and then we will check whether they say how well they satisfy these requirements. The first one is protection. It means that we should be, when we are making this translation from virtual address to physical address, or from whatever, so in the protection case, it means that I have this physical memory, and then I will have these different processes allocated to the physical memory regions next to each other, yet they should be protected against each other. Okay. The second thing is fast translation, meaning that any translation from virtual address space into physical address, okay, this should be fast. Okay, so that means that you cannot use very fast. You cannot, if I'm making this translation using a system call, then it's out of the question, because then it's way too fast. Okay, and then finally, whatever we deal with the context switching, this is something that you have to do very fast. So it means that I should not be I should be able to do this really fast. Okay, and any overhead should be low. Okay, for example, in the case of a PSET, that is, we talked about the PCB, and in the case of PCB, we said that there are three components, right? Address space, okay, CPU state, and the operating system resources, right? And in the case of address space, when I first discussed this, I said that it's essentially saving this. And when you first do this, you would say that at every context switch, all the physical memory that's allocated to one process is saved on a disk. Okay, but this is not possible because it will take ages to do this, and basically we will see that how in a system that's doing this context switching should avoid this and do this in a different way. So we have seen what the virtual address looks like. So I will not discuss, but note that when you do an executable, this is basically it's in the case of 64-bit system, is that huge, okay? And then here we have our instructions and the initialized variables. And what we mean by this is your executable. Of course, you should have the code, okay? So in the executable, you should have the code, okay? Plus initialized variables. What we mean by this was, if in your code, if you have int I equals 5, it means that it should allocate some location in here and put a 5 in this. And this 5, this initialized variables, okay, IB, this is basically this is part of the executable because that 5 it should be in here. And then we will have uninitialized variables. This is separate here, and we do not store the uninitialized variables. And these are things like an int, for example, j. Okay. In this case, all we need to do is we need to allocate some space, but there is no initial value. And this can be huge. It can be huge arrays, for example. And in this case, we don't have to store a lot of zeros here. Instead, we just say that the uninitialized variables, okay, just allocate this much space. That's it, just one directive. And this is done, this would keep your executable very lean because you don't have to store this, but at runtime, then you can just allocate these spaces in that. And of course, we have the stack. So with the memory management unit, the idea is here we have our virtual basic memory, and here's our physical memory, and the memory management unit then they should map these virtual addresses into. So these are the virtual addresses, and this is the physical addresses. It should do that mapping in a fast way. Okay. And we know that usually we do not map the whole all the virtual memory into the physical memory because it's way less. So we should only be mapping the portions of the stack, the portions of the code, the portion of the variables that are being used. So the idea is as follows. So here's our CPU, okay, and the CPU basically works with virtual addresses. And we have the memory management unit, and we should then do a translation. So this translation is from virtual address into physical address, okay? And then with the physical address, then we should get access to the memory. And then we had this TLB, which is translation look aside buffer, and we have learned that, and this TLB is essentially, so what's a TLB? This is it's a cache, okay? And what does it cache? Well, it caches information that helps us to do this translation from VA to PA. This is not basically exact, I will clarify this, but it basically caches these translations such that, if when we are accessing this VA to PA mapping, then, once we access them, then we put a copy into the cache such that the translation becomes much faster, and this exists this is actually on the same chip. Here are some basically simple forms of memory management systems. We will be discussing paging in detail, but what we discuss here had been used in earlier systems, and they may still be used in certain embedded devices where we have much limited resources. Okay. The first thing is option is we can split the physical memory into partitions of fixed size. Okay, in this case we have say 1K partitions, and each partition is essentially what a single process can fit in. So the virtual memory, okay, for each process is essentially 1K. Okay, and what you do is, what this means is, your addresses, the virtual addresses, then goes from 0 to 1K. Okay, and that's what we have. Now we can store a base register, and this, for example, if I have a process that's using partition 3, then we take its virtual address, which is between 0 to 1K, and then we add it to your base register, and then this is now your physical address, and with that I can access the physical memory. Now what's the advantages and disadvantages of this approach? So the advantage is, we can do a fast context switch, meaning that, I have that base register, so by updating it, then I can make a context switch very fast, right? And the memory management code is pretty simple. You just locate an empty partition, then you have a new process, and then just allocate it as such. Now, what's the disadvantage? The disadvantage is internal fragmentation. What we mean by this is, so this is my, these are my partitions, okay, and each of them is 1 kilobyte. And in this case, what this means is I can have at most 6 processes at any time. Whereas, like if I have a process, for example, that's only using this much of this, okay, and then I have another process that's maybe using here this much, okay, another one is using more, okay. So with this, you can see that if I add up the, if I can look at these empty spaces, okay, so this is empty, that's empty, this is also used, okay. If you add up all these empty spaces, you can say that, well, there's quite a lot of space that's empty, but you cannot actually insert another process into the system, okay. So all these locations are basically wasted, okay, and we call this internal fragmentation because unused memory inside or inside the partitions. So this is a disadvantage. The second one is static partition sizes. What it means that, if I have to set up, like if I set up 1 kilobyte partition size, then I can fit, for example, 6 processes. Okay, but what if this means that my any process should be able to fit into 1 kilobyte address space? If I need to have like a support, like a programs that has 2 kilobytes, okay, then I should set this as such, and but as a result, I will have only three processes. Okay, so this is it means that a single size is not approved for all programs, but in this case, you don't have any choice. Either you can, have a larger partition but support only fewer processes, or vice versa. So we can resolve this using variable partitions. And in this case, we can, for each process, we store the base of the memory, physical memory, and plus the size of a particular process. Okay, and what we do is, for example, imagine that I have this partition 3, and say that if this is your, so it may be starting at 3 kilobytes here. So this is what we have, 3 kilobytes, and if this size is say 2 kilobytes here, then the limit register is 2 kilobytes. Okay, and your offset, the virtual address, is then between 0 and 2 kilobytes. So by just checking this, then you can see that, for example, if the virtual address that's incoming is greater than 2 kilobytes, then you will get a protection fault. That means that you're trying to access to locations beyond this. Okay, and by adding this, then you can actually get your physical address. Now with this, you can see that this is really nice. This provides more flexibility to us, but the problem is, you can have in time, you will have these regions, okay, in between, like these. You can imagine that you start from the beginning, you allocate some space, and when that process quits, then that whole partition is then becomes black, right? And in the meantime, you'll have these black regions all over, okay? And with these black regions, now you can see that like the total all this is, you say that if this total is 1.5 kilobytes, okay, and you have now you want to have a new process which only needs 1 kilobyte, okay. In that case, well, you have the memory, but you cannot fit in this. So this is what we call external fragmentation. In the external fragmentation, it means that unused space or memory in between, or we can say the external to partitions. So this is the problem that we have. Of course, you can say that, well, if I am in a position, then I can move all the partitions back and forth, but that is, you can say, a costly operation, and you don't want to do this over and over. And what you will be focusing on is the modern technique called paging. And in paging, we know what a page is. So this is our virtual memory. We split this into pages, and this is our physical memory. We split into pages. And note that the physical page is also may also be called the frame, or sometimes page frame, or you can say it in a physical page, whatever it is. But so this is what this is. It's the same thing. The idea is you have these pages, and these pages are of a certain size. It can be 1 kilobyte, 4 kilobytes, sometimes 4 megabyte, but they have the same size on both the physical memory and the virtual memory. And with this, then with the memory, remember that when we have a process, we will have like the virtual address spaces. This is the virtual address space of P1. This is the virtual address space of P2. And this is the virtual address space of P3. Okay, and they all have different pages. And with the memory management unit, then they share the very same physical RAM next to each other. You can see that we have allocations next to each other, but yet they are assigned to different processes. So this picture, it kind of shows you how the virtual to physical address translation happens. And just show you, this is we have learned this, but this is just a reminder. So if this is my virtual address, okay, and what I do is I compute the pages, okay, and with respect to pages, then you can see that I can set some of these as the page offset, okay. This depends on this. In this particular case, for example, how many bits do I have as the page offset? In here I have 12 bits, okay, for the page offset. So what's the size of the page of a single page? It's to the power 12 bits, okay. So this tells you within a page where you are located. So if this is a page here, then where are you? Is it this? So this is what we call the offset, okay. And what we do is we split this virtual address into two parts: the virtual page number, which we call VPN, okay, and the page offset. And with this, so this is one virtual address. I split this, and I have this VPN, okay, and then here I have the page offset, or sometimes you can call it virtual page offset, but it doesn't matter because it's not the same with the physical memory. Then here we have this crucial thing, which is a page table. A page table is essentially an array, and this in this array we use the VPN as the index to the page table. And from this, if the corresponding like this says that, for example, say the 7th virtual page is mapped onto whatever, like this is my physical memory, is maybe mapped to 2, okay. So you can say the physical page number, okay, is then given here. We call this also physical page number, okay. And given this physical page number, PPN, if we append it with the offset, which is what we had here, then this will give us the physical address. And with this physical address, then I can access my physical memory and get the data from here. And each of the items that I have in this page table, it's called a page table entry, or a PTE. Okay, you have any questions on this? This is a reminder, but yet nevertheless, if you have any questions on how this address translation works, speak up now, otherwise you'll be lost.
Hocam, can you repeat how we get PPN?
How we get PPN? It's pretty simple. You take the virtual address, right, and then you dissect it into two. The page offset, okay, which tells you where you are in the partition, and then the rest here. This is what we call this is VPN. Okay, it's saying that in my this if this is my uh, virtual memory, okay, then I have split this into a lot of virtual pages, okay, and in this case, for example, this is virtual page 0, this is virtual page 1, this is virtual page 3, 2, 3, and etc. Okay, and the page table essentially stores which, like say, virtual page. This is what I call a VPN. Okay, and it says that which virtual page number is mapped onto which physical page number. Okay, and once I get the physical page number, then by adding this offset, basically tells me in here how much it's basically where my location is. Any questions? So what's this page table entry? So the page table entry is what we have in this page table. Each of them is a page table entry. And this depends on the CPU architecture, but it has this following thing. So the first thing is, if we contain the most essential ones, we have a valid bit. Okay, the valid bit is saying that whether that, remember, this is indexed with the VPN. Okay, so for each virtual page, there's a corresponding page table entry. And when we have for this one, if the valid bit, this can be 0 or 1. Okay, if it's 0, it means that that particular page is not yet brought into the physical memory. Okay, we will discuss this then if we create a page form. If it's 1, which is what we'll discuss here, then it means that that particular virtual page is mapped and brought into the physical memory. So then here we have the page frame number, or PPN, physical page number. Okay, and it stores this. It says that for this particular VPN, this is the PPN that's corresponding. Okay, that's it. And along with this, then we have a number of bits. This again depends on the CPU architecture. Things like protection bits. Basically, it says that whether that particular, it's like the read, write, access bits for your file. The same idea. In the protection bit, it says whether a particular page is readable, writable, or executable. For example, if you look at the code section, okay, that code section is, for example, readable or it's executable, but not readable or writable. Okay, on the stack, for example, the stack is writable, readable, but not executable due to buffer overflow attacks. Okay, and etc. And then we have two other things. Again, this is just sample. One of them is reference bit. The reference bit indicates whether a page has been accessed, read, or written. And we will be using this when the memory becomes full, and we will be hunting for a page to kick out. Then that's basically when we will be looking at these reference bits. Okay, and M bit is the modified bit, which indicates whether a page is dirty or modified. And this happens when we have, you bring in a particular page into memory, and then if you update it, then that means that if you had brought that page from a say file, then if it's modified, then in order not to lose the content, you should be then saving it back onto the file. If it's not modified, then when you're discarding it, you don't have to write it because an exact copy of that one is already resides on the already resides in the file system. Okay. Usually, at every say 100 milliseconds, all the reference bits are cleared. Okay, and then if you have another access within the next 100 milliseconds, then it's set again. So this is something that's just 1 bit, but you can clear this at regular intervals to have a feeling how recently that particular page has been accessed. So we'll discuss this. So what's the advantages of paging in relation to, say, those partitioning idea? The physical memory management is simple, okay? And you can see, like in this case, we are not like in our page table. We have a page table here, okay? And the page table. This is a mapping from v virtual page number, okay, to physical page number, okay. The page table does not do the following. It doesn't say virtual address to physical address. It doesn't do this, okay. But once you have this VPN and PPN, then by adding the page offset, by concatenating the page offset to its right-hand side, then you can get the address. But the main advantage of splitting into pages is it keeps my page table in a reasonable size, okay? So I don't have to worry about it. So the nice thing is there is no external fragmentation, meaning that you allocate things in terms of like different. So any page here in the virtual basically memory can be mapped onto any physical any page in the physical memory. That's nice, and we don't need to allocate pages in a contiguous fashion, meaning that in my virtual memory maybe I have like 1 and 2 mapped here. They are contiguous, but in here they may be mapped onto different regions, okay, different pages in the physical memory. I don't have to do them in contiguous. And allocation can be performed at defined granularity. This is at the level of page size, okay, and this is nice. But there is internal fragmentation. Internal fragmentation happens. It's because, remember, since all the allocation is being done in terms of pages, even if you're using only 1 byte in a page, then you should be allocated a whole page for you. So internal fragmentation. And you can see that, for example, if I set my page size small, okay, then you will have less internal fragmentation, but the page table will be larger, okay. But if you set your page size large, for example, say 4 MB, then your page table will be small, but internal fragmentation will be much higher, okay. So you should be able to basically understand how the dynamics works. So these page tables are very important. And note that, well, we need to keep these page tables in the physical memory, right? Because they are doing this. I don't want to store this. And in here, for example, this is my say P1 for so for a particular say page process A, okay. And for process A, in one of the pages in my physical memory, so this is my physical memory, then this is where my process A's page table stores. And if I have another process, then I have another one. So for each process in my system, I need to store its page table in the memory, because remember, for during each memory access, I have to be accessing the page table every time. So this means that, like, if I have, like, let's discuss this. If I have no virtual memory, then all the addresses, like all the addresses, you send the address and then you get the data. Okay, this is nice. So all addresses are actually, you send the PA, the physical address, okay, and then you get the data. In the case of VM, however, it works as the following. So you have a virtual address, okay, and then with the virtual address, the first thing that you should do is you should access the memory and you should access the page table, okay, the corresponding one with the indexed at, for example, with the VPN, okay. And then once you have this, Then with this, then from this you can get the ppn. Okay, this is the colon just in here. Okay. So this whole thing is then this, if this is in its ppn, and then plus you add your page offset to this. Okay, and now this is your uh, physical address, and with this one then you can go ahead and get your data. Okay, so this means that I have two in the virtual memory system. I have two memory accesses. One to access the page table, okay, and then two to access the data. Okay, now this is like twice the cost of the physical memory system, and this is very costly. Okay, so like I say, if your access to physical memory is say 100 milliseconds, then this means that I have 200 milliseconds of delay, which is, it's nice, but it's slowing me down quite fast. So then the idea is, if I can cache the page table into basically somewhere in the CPU, and this is what we call a TLB, translation look aside buffer. Okay, and then it will make things much easier, because instead of going all the way to the page table in the memory, I can access the TLB and then do the translation and then immediately go for the data. And in actually in the most like in Intel processors, and I think this is true for AMD as well, they have separate data and instruction TLB, so they have basically separated that. Okay, and what they do is, so let me do this here. So what the TLB does, okay, TLB, it's a cache. Let me see if I have a regular cache here. So if I have, in the case of a cache, okay, in the case of a cache, you give the address, right? And from the address, if the data is cached at that address, then you get the data, okay, the cache data, okay? In the case of a TLB, this is also a cache. So TLB is a cache for page table. It caches page table. Remember, and what a page table was? A page table was a mapping from VPN to PPN. Okay, and hence in the case of TLB here, what we do is we send the VPN, okay, as the address, and we get the, well, like it's not PPN, this is PPN, but this is actually the page table entry here, okay, in which we expect to see the VPN. So from the VPN, we get the page table entry, which also includes hopefully the PPN, okay? This is basically how the TLB works. And hence, once we do this, if this is your page table, okay, which is in the physical memory here. This is your physical memory. And here's your CPU. And in the CPU, you have this TLB cache. Okay. And what you do is from this page table, which can be huge, okay, you basically read out like the values that the PTE is here. For example, you may be caching them as you access. You may be caching the lines from the page table into the TLB, okay, as they use it, and such that when you come here with your from your uh, virtual address, you give the virtual VPN, okay, and if it's in the TLB, it immediately gives you the page table entry from which you can then read out the PPN, and then append this. From this you can get the physical address, okay, and then from this you can access the physical memory. So it works like the TLB is a cache. It's usually implemented as a highly like associative cache. We have discussed this in computer organization. And if you have a TLB miss, which means that then you actually have to go all the way to the main memory and then basically read the corresponding page table entry and then make a copy in the TLB. So when you're loading the TLB, what we have seen is like you can load the entry in an automatic way with the hardware. So the memory management looks for the particular TLB for an entry. If it's not there, then it will create a TLB miss, and then it will go all the way to the page table, okay, and then reads this and then makes a copy into the TL. That's the automatic hardware way. But we can also, like, it's also possible to do this in a software way, where when we have a TLB miss, then you can actually this kind of cause this as a trap into the operating system. So it will handle this as if it's a page fault, and it can look at the page table entry and then loads it into the TLB entry. So why may what's the pros and cons of these two different basically uh, uh, mechanisms? Well, it's if you have a software managed TLB, then the operating system can basically dictate the page table format. Okay, and it gives a lot of flexibility to the operating system designers to design memory management policies. But when we have a TLB miss, then updating, like the modified reference bits in the page table entry or bringing this, there's a lot of performance impact because, in the previous case, it was done all by hardware. Now you'll be running some operating system code to handle this. So that's the downside. So how big are these page tables for a process? And here we have, let's do some calculations here. No, let me do just in here. So let's create that we have a 32-bit system, okay? And let's say that my virtual memory is 2 to the power 32 bytes, okay? This is actually 4 gigabytes, okay? And so we see that the page size is 4 kilobytes, okay, which is 2 to the power 12 bytes, okay. And as such, now, like how many, like what's the page table size? So let's look at from our virtual address part. So our virtual address is 32 bits, okay. Since the page is 2 to the power 12 bytes, it means that I'll be using 12 of these bits as my page offset, okay. And the remaining, which is 20 bits here, the 20 bits here, I will be using them as my VPN, okay. So based on this, then I will say that in my page table here, this is my page table, then it should have 2 to the power 20. So remember, I'm using the VPN as my index, 2 to the power 20 page table entries, okay. And so that's we know this. And what about the size of each page table entry? So this is my page table entry, okay. So what's the size? Well, let's look at, what do we have in here. In here, this, it depends on, but at minimum, I should be able to store my PPN here, okay. And plus a valid bit, the other things can be, you may have a few other bits, but at minimum, I should have the number of PPN plus one valid bit. Okay, this is the minimum. And what's the size of a PPN? Well, it depends on how much physical memory you have. So we can look at the physical address, okay? And let's say that if my physical memory is, say, 1 gigabyte, okay? So this is 1 gigabyte. Then what does it mean? Well, it means that I have 2 to the power 20 bytes, okay? So the physical address is 20 bits, okay? And with this, okay, I can then split this, and the 12 bits of this is your page offset, okay? So this is, no, not 2 to the power 20, but this is 40, so 30, okay? So it's to the power to 30 bytes. So this means that, as the PPN here, I should have at least 18 bits. Okay. So this means that for PPN, I need to store at least 18 bits plus 1 bit plus a number of bits, right? So the size of the page table entry, usually you want to have this page, the size of PTE, as a multiple of 2, okay? So in this particular case, you can say that the P size of the PTE should be at a minimum of 4 bytes. Okay, it's 4 bytes because it doesn't fit in 2 bytes, and 3 bytes is odd, so the minimum is 4 bytes. So that means that the size, okay, of PT, okay, that's 2 to the power 20, okay, times the size of that, which is 2 by 2 to the power 2, okay, and this is what? 4, how much? 2 to the power 20 is megabyte, this is 4 megabytes, okay. So what we do is like we have like for each process, the page table requires 4 megabytes, which we should keep in the physical memory, which is quite a large. Okay, so if you have, for example, 100 running processes, that means that I have to allocate 400 megabytes of my physical memory just for the page tables, and that's a lot of extra overhead. And so the solution that we have is we want to keep some of those page tables on the disk, especially when they are not being used. So we will be discussing that also. Let's remember our 3 requirements for the memory management. Isolation, so it means that we have to ensure that the phone process cannot access another's pages. Why? Because since we are maintaining these page tables, so here's my page table 1 and here's my page table 2. Okay, so if I ensure that this ppn here doesn't appear in the page table 2, if I have 3 here, for example, let's allocate the third ppn to process 1. If I do not have 3 here in the page table 2, it means that, well, I have complete isolation. And I can do this because the page table, I can keep this in my kernel space, and hence only the operating system can handle this. Okay, so we can have then completely disjoint physical address spaces. And the translation is pretty fast. It's because we can use the MMU and the TLB that's caching the recent virtual to physical translations from the page table. Then it's basically fast, and we can have fast context switching. Why? It's because remember that I said that in my case this is my physical memory, and in my physical memory I can have the page table 1 here, and I can then have a page table 2 here, and all I have to do is I can maintain a page table base register, okay, which I can update in the case of a context switch. If I'm running basically the process 1, then I can set this to page 2, so that now I'll be using my page table 1, and when I make a context switch, then all I have to do is point this to this new page table. Okay, so I don't actually have to save the whole address space by changing the page table that I'm using, which I can do by just updating one register. Then I can make a context switch in terms of. So let me just go ahead a little bit more, and then I'll leave the video. Okay. So what happens when you have a page that's not in the memory? That's what we know. It's a page fault. And the second problem is, and we'll discuss how that works. Second thing is the page tables. They take up a huge amount of memory themselves, so we need to solve them as much as possible. So what happens in the case of a page fault? So in the case of a page fault, well, what we do is, remember, let's look at the page table entry here. The page fault happens when this valid bit is 0, okay? And when the valid bit is 0, and this is called a page fault, but sometimes page fault indicates like the fault, there are 2 things. It can also occur when you try to, for example, write into a read-only page. So you also check with the protection as well. Okay, and what we usually call the protection fault. And what we do is the following. Uh, in the case of a page fault, that's an indication that we should bring a particular page into the memory. So let me have a break here, and in the next hour we'll discuss how that works, which is called demand paging. Okay, so what's demand paging? When I first learned, the first thing that I had in my mind, what happens when you run a program, right? After you learn this address space and so on, you think that when you run it, the first thing it would go into the disk, it would read the whole executable, put into the physical memory, and then after that, you then start from the first line, right? That's what it is. Well, guess what? That's not true. You do not read an entire program into the memory at once and then start execution. And how does it work? Well, it works as following. You don't do anything. What you do is you try to read, if you have in your space, you go ahead and you try to fetch the first instruction of your executable. And guess what? All that when I want to fetch the first instruction here in your code, it has an address. You split it, you VPN, you go to the page table, and in the page table, initially, okay, so the page table. Remember that what I draw as page table here. This is a replication of the virtual address space, right? So if I have a code in my virtual address space, it means that the entries that I have in here correspond to the first correspond to the entries for the first VPN, the virtual page numbers. Okay, so for each of them, I can have a different page in here. So they reflect this. The page table reflects the virtual address space. So when you try to fetch the first instruction, you have the address, you go into the page table, and initially, let's look at this valid bit. The valid bit of everything is 0. Okay, nothing is brought into the physical memory yet. Okay, everything is. But what we have not discussed was in these page table entries. Remember our page table entries here. And I said that there's this valid bit, and if the valid bit was 1, then I would have the PPN plus maybe other bits here. Okay, so I'm neglecting the other bits for the time being. Okay, so it's basically valid bit plus the PPN. That's nice. And what if the valid bit is 0? When the valid bit is 0, then in this space we store information on how to create that page, how to bring that page into the physical memory. Okay, and in the case of, for example, the executable, what we say is, well, in this particular page, for example, we can say that go to disk block, say number 52. Okay, in that 50 seconds basically block, then you have your information. All you have to do is read it from the disk, bring it and put it into memory, and after you put it, then update it. Okay, that's the idea. So with this, it applies to code. Sorry, it applies to code. It applies to access to variables. It applies to stack, etc. Okay, so essentially, when you try to, for example, to access the first byte, then you will be accessing this VPN 0. Okay, and in this case, it will be saying it will create a page fault. As a result, you will go and it will be the page fault. You'll say, okay, let me create this with this block here, and you allocate some page in the physical memory. So use my physical memory, and maybe you should say that let's allocate a page, a PPN here, and you allocate it, you bring this into this location, and then after that you update your page table entry. And after this, essentially, instead of this, I will have 1 here. Okay? So this goes as such. What this means, what this implies is we call this demand paging, meaning that in your executable, if there's a portion that is that has the code to print for my PowerPoint, which I never use, then that portion of the executable is never loaded onto the physical memory. Okay, you only bring the portions of the code, the portions of the data. Imagine, you have these initialized variables. Maybe, some portions you never use it in your case. In that case, those portions remain on disk. They are never brought into the physical memory, which is really nice, right? You just bring in the parts that you do this. So that's what we call demand paging. You bring a page into the physical memory only if it is accessed, only if it's necessary. So, as such, you can see that in the virtual address space, there will be certain black regions, which we call holes, okay, uh, which are not brought into the physical memory. And I can see that this is my virtual address space. And you can look at the page table, okay. And as I said, the page table reflects the virtual address space. In this case, for example, if you look at the portions of those black regions, okay, so in this case, for the portions that are black, okay, we have, for example, 0 as valid bit. For the portions that are like blue and like all these different portions which are mapped onto the physical memory, then we have ones. So you can have a lot of these locations, the black regions, which are basically used as such. So these holes that we see are basically, these holes can correspond to three kinds of basically pages. The pages that are on the disk, like for example, the portion of the executable, okay, that you have. Or maybe we will be learning, like I think in the next 2 hours that we may be sweeping out some of the things onto the swept part. And so when you sweep them, then you again mark in your page table entry that this page is swept onto the disk. If you want to get it, that's it. So that's what we have, but the pages on the disk. Okay, or the pages that have not been accessed yet. Okay, and for example, imagine when you allocate a new memory, and you can see that this is happening in the case of, for example, heap. If you've ever done like you malloc, say 16 gigabytes of space, and you'll be surprised how fast it returns. Okay, it's really fast. And you would say that, what happens? I mean, like you cannot even zero something in that short amount of time. Well, guess what? What you do is, like, imagine, say, this is my space, and then you allocated a, say, 16 gigabyte of space, okay? And, well, instead of going all the way and then, for example, zeroing on all of them, what you do is, in your page table, when you do a malloc, in your page table, what you essentially do is you say that, I have, say, this many entries to corresponding to this. And then instead of before, it was all those pages were not accessible. Okay. Now you change their access protection, so they should be able to readable or writable, but they're not created yet. There's no physical. So what instead, like remember in the case of the executable, we said that if all those valid bits were 0, which is the case when you malloc, you set all the valid bits are 0, but do we map them onto some disk block? Well, no, because they should be mapped to something like that 0. Okay, if I need to create those pages, then all I have to do is read a page full of zeros and bring them. So instead of the disk, you can say write 0 here. And what this means is, until all those pages, you just change the page table entries, and then you do nothing else. When you would start writing or reading these pages here, then you will create a page fault, and in that case, then all those particular physical memory, physical pages are allocated. They are zeroed in, they're zeroed, and then you can access it. Okay, so that's why malloc returns really so fast. Okay. And there can also be pages that are invalid, which is, for example, when you access 0, 0, which is like in the previous cases, like this this can be slightly confusing because like in actual space, you remember that, at the 0, 0 to 0x 0, these pages are actually uh, do not belong to your process, and there's a basically protection fault. Okay, so all these pages that are invalid, they are also be marked as as a whole, and when you have a page fault there, then it will kill the offending process. Okay, so initially when you start, when you access a code here, okay, then you reference the, like imagine, like you first access it and you create a page fault, you read the missing page from the executable, you add it onto the page table, and so on. So as over time, more and more pages will be brought in from the executable in the as needed, and your stack grows as such. And even when you you're using your stack, when you want to push something or access it, then it implicitly creates a page fault, and in that case, then you do whatever that's necessary. So as I said, when we have a page fault, if you have the executable file that the code segment and the initialized variables, then you should read this from the executable file. Okay, so you map them onto your disk block. So remember that on my description of the PTE, and I said that this is 0, the valid bit is 0. Then here I would say that if it's, for example, if it's the code segment, and I can say that this is, go to, oh, sorry, this is in the case of the here I can say that you go to disk and 117. Okay, and the initialized variables, again, I can also map them onto that. But the uninitialized variables and the heap, well, where do we map them? Well, we shouldn't be mapping them onto the executable because we do not have this, and we should map them onto a virtual zero page, right? Okay, meaning that you can imagine that there is a disk block that's full of zeros. Okay, and whenever you access it, you can just say, oh well, I'll just bring it into memory, but this is not needed. That's why we have split up the initialized variables from uninitialized variables, because the uninitialized variables should not be part of the executable. Okay, and when you have a global variable in the program, then only when the first process first accesses, then you allocate the corresponding page and then access it. Okay, so this is the whole thing. You create the page fault when you first access it, and it realizes that based on the page table entry, it maps to a zero page. It allocates a new physical frame in the memory and sets all the bytes to 0. Why? Because that particular page may have been used by another process before. Hence, in order to not leak any information from that process, you should set them all to 0. And then we map bring it to the address space by updating, updating the page table. Okay, and after updating now, you can see that after update, then I will have my valid bit as 1, okay, and then I will have the corresponding PPN. And before what I will have is the following. Before, it will be 0 as valid bit, and then here I would say that it's a 0 page. That's it. Okay, that's what we do. And what about the heap? Well, malloc is just wants to map new 0 pages into the address, and then as we access them, it will create page fault, and then the physical empty pages will be allocated as such. If you have any questions, please go ahead and ask. Otherwise, I'll move ahead. So with this, you can see that since I'm mapping them, I can do a couple of tricks to minimize the footprint of processes. And for example, on your system, you will be running the same shell code over and over, like everybody using it. And the code portion of this is actually the same, right? And what you can do is you can map them onto the same physical pages here. And what this means is, even if you have 50 basically processes running, 50 shells running, the code, you will have only one copy of the shell code in the physical memory. But the other portions, for example, the stack is probably different, right? Or the variables, those portions will differ in time. So they will be, you will have separate copies. I will have, for example, two different initialized variables here, okay? And this is, for example, for shell number 1, and this is maybe for shell number 2, okay? But the code is shared, and this is really nice. So you can see that like we have done this in the case of inter-process communication with shared memory, and we have seen this shared memory get, attach, and detach. And what it essentially does is it says that it marks the certain regional memory that's shared across multiple processes by just pointing them the page, making their page tables the same. Okay. And if you make them readable, writable, then it allows you to create that and as such. And in the case of a memory mapped files, well, guess what? It's like remember what a memory mapped file was. When you memory map a file, you map it into your address space, so it appears the file contents appears in your memory, so you can do pointer arithmetic in that instead of doing a seek and move and forward, etc. So what you can do is when you're memory mapping files, it's essentially the following. So this is your page table, okay? And in your memory, then let's say that I want to memory map a file, and that file has a block here. Say that block 5, okay? And what you do is in my page table, I have my executable and etc. When you do a memory map, what you're saying is I'm adding a new entry, like into some portion of my address space. I set this to 0, but I say that it's it's disk, okay, 5, okay. And what this means is if when I access this, well, it will go ahead and read this into the physical memory. Okay, so let's say that this is my now physical memory. Okay, so you bring this into your physical memory here, this whole data, and then you update the corresponding page table such that after that you will be accessing the disk by working on its copy in the physical memory. And when you close it, all you have to do is save this back onto the same disk block. Okay, that's it. So you can see that with this demand paging, you can map a whole file onto memory. And what's nice is you don't have to read. It can be a huge file, right? It can be a whole big database, and this is actually what and once you map it, you don't have to worry about how big the file is, because you know that only the portions that you're accessing will be brought into the physical memory, and it's as simple as that. Now let's go back to fork. Remember that when we were forking, we said that we duplicate the process, we duplicate the address space. Okay, we duplicate the CPU state, we duplicate the address space, but operating system resources, they were shared. Fine. Now, when we fork a new process, and do we copy all the physical memory? Okay, meaning that when we fork, now do we double our memory usage because I have now a different copy of this? Well, guess what? I mean, so in most of the cases, the child process may not be touching most of the memory that the parent was using. For example, we have seen cases where the child, for example, does an exec immediately after a form. So in that sense, duplicating that is actually very costly and useless because you'll be overwriting the whole address space due to this. So what do? Well, welcome to copy on write. Here's how it works. So here's our parent, and the parent has a page table. Now in this case, I have drawn the physical memory in the horizontal form. Don't get confused. So this is the virtual memory, okay, and this is the parent's page table. So this is how it works. And after for, what we do is we create the child, and this is child's virtual memory. And what you do is you copy the parents' page table as child's page table. Okay? And now they both point to the very same thing. Remember, but as a result of this fork, I actually have not duplicated my physical memory usage. But as it is, it doesn't make sense because in this case, the child and parent, they are both can screw up each other's memory space. If child updates something, then it will also be visible in the parent. So it kills the whole idea of the different processes, right? So after this, what we do is we update their permissions into read-only mode. Okay, read-only. Okay, for both child and the parent. Okay, this means that after fork, if both the parent and the child, if they just access those pages as in the read mode, then no problem will occur. Okay, because they're just reading, they're not updating it. That's fine. Problem will occur only if one of them decides to update anything in that physical memory. So here, when we try to write something, say that this child, for example, wants to write this location. Okay. Now what happens? Well, in that case, when I'm trying to write that, then it copies this. Remember, it copies this. It makes a duplicate on this page. Okay. And then after that, then it updates that particular page table for this. Okay. So it changes to the read write. And after this, the parent's page is also marked as read write. Okay. So this is a now switched. So with this, you can see that I will be physically duplicating pages only when parent or child decides to write on it. That's why we call it a copy on write. Whenever there's a write, make a copy. Okay? And with this, by default, all the pages are shared, and only the pages that are not being written, only the pages that are being written are duplicated. So this is the maximum way of minimizing the footprint of the parent and the child. Okay, so that's really nice. What about the page table size that we have discussed before? Remember that like this is how the paging worked. So we had the virtual address, and here we had the VPN. Okay, and this is the page offset. We use VPN into your page table. We get the PPN here. Okay, and then we append it with the offset, and we have the physical address. And with this, then we can access the page. Okay, and we said like in the examples that we have done, we said that this may cost this will cost 4 megabytes per process, which is fairly large. Okay. Now, one way to basically minimize our usage is we can split this into multi-levels, meaning that given this virtual address, so this is the offset that we set aside, and in the virtual address we split this into two parts. We can say that this is VPN 1, virtual page number 1, and virtual page number 2. They can be same size or different size, it doesn't matter. Okay, and the first one, which we call is the page table, it's the primary page table. It tells you so we have two levels. The first one, this portion tells you which page table should I be using. Okay, so I have a number of secondary page tables. Okay, so let's say that, for example, imagine I can have let me do this example here. Say that this is let's say that this is 12 bits. Okay, and just for the fun of it, I will make this say this is say 9 bits. Okay, and then let me make this say 10 bits. Okay, 10 bits. So if I have 10 bits here, it means that in the primary page table, I will have 2 to the power 10 entries. Okay, and in here, I will have secondary page tables. And each page table will have 2 to the power 9 page table entries, right? And then how many of them do I have here? Well, I will have 2 to the power 10 secondary page tables. Okay? So what I do is, given the virtual address, I look at here, and then in this primary page table, it will tell me which page table, which secondary page table I should be using. So, for example, in this case, it may be saying that, it may you need to use this one, okay? Because I have 2 to the power 10 of them. I have 1024 secondary page tables. And then once I find them, then it will be the secondary page would say that, okay, in that page table, which one should I access? That's it. Okay. So this is more like the following. Remember, in the old days we had this Rex or encyclopedias, right? And in that case, the first thing that you would do is, and we had these letters like A to B, C to D, and etc. So given your, for example, your word that you want to look at, if you want to look for Albania, then you cut the first. Your VPN one is A, okay? Then you look for A, you pull it, and in that, then you would be looking for Albania, okay? Of course, in the encyclopedias that are produced, they still have this A, but they could have omitted the first A anyway, right? So you should have just look for Albania, and etc. So this is the same thing. This primary page table tells you which one that you should pull up, and the second one will tell you which page in that in that issue you should be looking for. And in that, then you will have this full page table entry in which we will have this PPN. Once we have this appended with the offset, then you will have your physical address here. Okay. So this is, you can see that with this one, I can now have like two level. And what's the downside and all this? Let me go here. The nice thing is with the primary page table and the secondary page table, in total, actually, if you look, compute the amount of space, you're not reducing it. Okay, the space, like let me go back to here. So remember, I had like 9 bits here and I had 10 bits here, right? So if I had a single level page table, then how many entries would I have? I would have 2 to the power 19 entries, correct? And then times the size of a single page table entry. This would be the size of the page table. What about this case? Well, in this case, I will have, like, this one will have a size of 2 to the power 10, okay? And times page table entry, okay? And what about the ones in the second level? In the second level, how many? I will have 2 to the power 10 second level page tables times 2 to the power, and each of them will have 2 to the power 9 entries, okay? And then times page table entry size, okay? So if you add both of them up, okay, this is bigger than the single level, right? Okay, so I haven't used much, and in fact, I made things more complicated. So as much as it looks, guess what? What do we gain from this complexity? Let me go ahead and we'll see in here. So in here, the nice thing is, remember, like when I had my page table or address space, okay, it's the same thing. You would have like your entries here, like code and etc. And then you will have these regions that are empty, okay, that are not mapped. Okay, maybe some usage here, and then that's again empty, right? And in this case, you can see that for the first page, for the primary page, I will have this empty thing, that's fine. But for the second one, like for the ones that I have here, I will have a corresponding second level page table. For this one, I will have another second level page table, or this one, a page table. But for these ones, I do not have to, for these ones that are basically not being used, if it's null here, okay, then I do not have to store the second level page tables, okay? And that will lead to a lot of basically shrinkage in the usage of page table in the memory, okay? So that's the nice thing. And second, we can keep this page table in the primary page table in the memory, which will be much less. Okay, in the previous case, remember this was 2 to the power 10 page entries, which is way less. Okay, and from this, only the ones that I'm using can be brought into the memory. And among them, actually, some of them actually, if I'm not using them, I can actually store them on the disk. And so I can page the page tables. I can use the same page fault mechanism to bring them on demand into the physical memory. Okay? So what you do is, if something is on disk, like let's say that I have a certain page table, and this is on the disk, and you can see that in this particular case, you can store this like in the first one. Again, you will have a valid page, you set this to 0, and you can see that like that this one from the disk is say you're on disk, say 7. So you can see that if you want to have this, then go to disk 7. Okay? So then you can do this, and you brought this, and you update the first level page table. Now it's in the memory, okay? And once you have this, then this one points to the beginning of the second level page table, and this portion here, the second level page, now you use this to index it, and then this will, from this you will get your PPN appended with the offset, and you will get your PA. Okay? Any questions? Are you still with me? I can see that there's a lot of chat going on. And I'm pretty sure that Denise is replying them because I'm not following them up. But if you have questions, speak up.
Could you repeat about the shrinkage of secondary patch tables?
Oh, the shrinking. Okay. So for the secondary page tables, okay, a lot of the, let's say, from the primary page table, a lot of them will have null. Okay, meaning that the second level should not even be exist. This is like your encyclopedia, and say that in Turkish, for example, there's a Q here. For Q, there is nothing starting with Q. Okay, so you just have a null, so you don't have anything. So you don't have to store the second level for Q, or like or maybe alpha, beta, gamma. Imagine you have all those things. In this primary page table, you can have A to Z plus Q plus alpha, beta, gamma plus blah blah, all the characters, right? But if I don't have anything in like for example alpha, then I do not have anything in the second level. Okay, so with these ones, only few of the second level page tables will actually exist, and and I can only bring the ones that I'm using into the physical memory, and if I'm not using them, I can keep them on the disk. That's how I can shrink the total size of the page tables in the physical memory. Is that clear, Kerem?
Yeah, thanks a lot.
Okay. Any other questions?
It's even possible to not allocate them, right? As long as we don't use them. So they don't
Yes.
have to take any space, actually.
Exactly. It's like
Which is much better.
Exactly. That's why I said if it's a null, then that's it. It doesn't map onto anything. Okay. So let's move on. Okay. So here's, as I said, like here's, for example, a simple case in here. So for example, if I have the 32 bits case here, okay, then I will have 12 bits for the page offset. Then I can have 10 bits and 10 bits for VPN 1, okay, and the VPN 2, okay. So, and then if I have 4 bytes per, like you can see that with VPN 1, I will have the first level page table. It will have 2 to the power 10 entries, and if the size of the PT is 4 bytes times 4, this is 2 to the power 12, okay. And guess what? And the same thing in the VPN 2, like I will have a lot of second page tables. Again, they will have 2 to the power 10 entries multiplied by 4, okay, and the size is what? 4 kilobytes. And guess what? What's the size of our page? The size of our page is also 4 kilobytes. That's nice. That's very sweet. Okay, so that means that I can page the page tables. Each page table fits in a page. And when you have a page fault, you look up the primary page table and then try to get the secondary page table. Okay, and we assume that this primary page table is wired into the physical memory, meaning that we always keep this in the physical memory because we access all the time. Okay, and it's little, so it's just 4 kilobytes. It's nothing. And then we try to access the secondary page table, and when you try to do this, you can get another page fault. Okay, and with this one, then you may access this. Then you'll then, once you bring this into memory, you look up with the VPN2 and get this PFN. I don't know. This is get the not PFN, but this PPN. Sorry. Okay, and then you get the physical address. Okay, you can see that what's the issue? The issue is the page translation can have a high overhead because it means that now I may be replacing in the worst case one memory access with one disk access, okay, disk copy plus a memory access. But when we have this TLB, these things are very seldom, and hence on the overall you really have quite a good speed up in the overall system. So this is the i7 memory system, and let's look at this. So this is, it has 4 cores. So in each core we have the same basically system, and we have discussed this in the computer organization again. You remember that we will have like the 2 ways: the instruction portion. So this is where we basically and the instruction. This is where we access the data. And we will have an instruction cache, okay, like in this case, and this is the data cache, and this is the 8-way set associated, blah, blah. This is the way for accessing data. And then with the memory management unit, which we do address translation, then we have the TLBs. Then we have 2 TLBs, the data TLB and the instruction TLB. And in this case, what we say is that this is it contains 64 entries. What this means is it stores 64 lines from the page table, okay? 64 VPN to PPN mappings, okay? And what about the instruction cache? In this case, it can store up to 128 lines from the page table. And you can see that this is L1 cache. Okay, then there's this L2 TLB, which is unified. It mixes up the data and instruction length, and it can contain up to this, and so on. And then from this, then you can, after this, then you can compute the physical address, okay, and with the physical address, then you can access the cache. So we have gone through this in computer organization. I will skip it. This is just a reminder. Okay. What are we doing? Okay, we have 8 minutes, so let's look at this. So let's say that we have, say, I'll just go through here. Okay. So again, this is a refreshing of computer organization, and this is the big picture, okay? And this is the one that's happening in i7. So the virtual address is 48 bits, okay? And the page size, in this case, it supports 2 different page sizes for this part because it's 2 to the power 12 bits, which is 4 kilobytes. Okay, so we have this, which is virtual page offset. It's equivalent to, by the way, physical page offset, but so don't get confused. So we have this 36 bits as VPN. Okay, and with this 46 bits, then we access the TLB. And in this case, you have to recall how a TLB works. It's a cache, okay? And from the TLB, I will skip those portions. From the TLB hit, okay, if there's a hit, it means that, then I can read out my PPN. And in this case, in my, and then you append it with your physical page offset, which is the page offset. And in this case, my physical address is 2 to the power, my memory is 2 to the power up to 52 bytes. Okay, this is how big my physical memory is. Okay, so you cannot put in more than 2 to the 50 to the power 52 bytes into your machine, no matter how rich you are. Okay, that's the limit. And in the case of paging, it does a 4-level paging. Okay, and remember I have shown you like 2-level primary and secondary. And guess what? In this case of i7, it does it at 4 levels. So here we have this is what we call, this is equivalent to page table base register, meaning that we change this value, this pointer, when we make a context switch. We have one value for each process. And we split this 36 bits into 9 bits. So we'll have VPN1, VPN2, VPN3, and VPN4. This first one, okay, then we get this, and this tells me how many I will have. So from this second level, remember, from second level, I have 2 to the power 9, which is 512 copies of second level page tables, okay? And in the third level, how many do I have? I will have 512 times 512 possible third level page tables. And in here, I will have again 512 to the power 3 possible fourth level page tables. And only in here, I can get the PPN. Okay, the page table entries here just point to the beginning of the next level page tables. That's it. Note that in this particular case, okay, and this is the, again, the actual data sheet for the page table entries, okay, and we have 3 of them. Let's go back. So for these first 3, okay, we will have a separate format, and this is the fourth one. So for this is 1 to 3. So for level 1 to 3, this is the format, and this is the actual thing. Okay. Now, so this is the P. Okay. This is the valid bit. It says whether the child table present in physical memory or not. Okay. So if it's 0, which is it's not invalid, then all the data here basically is stored by the disk. You can say you can go to disk 52, or you can say that it's a 0 page. Whatever you wish, this is all is as such. If it's 1, meaning it's in the available, then we have like all these other things. Like, let's see what we have. So first we have this page table base address. This is essentially the PPN, except that this one is pointing to the next level page table. Okay, and how many bits do we have here? We have 40 bits. Okay, and then along with this, we will have, you can see this is read only or read write access permission for all the reachable pages. Okay, and whether we can access this in user mode or kernel mode. Okay, and this is, you can see that we split the virtual address space into user space and the kernel space. So with the ones in the kernel space are marked with this supervisor mode, or like the cache policy, write through, write back, and we call this the reference bit, okay, which is set on reads and writes, okay, and the page size. In this case, the page size can be set as 4 kilobyte or 4 megabytes which is defined on for only level 1 PTEs. Okay, and the page table physical address is 40 most significant bits. Okay, and as a result, basically all the page tables are aligned at the 4 kilobyte boundary. This is because we are working at the page table level. And the last thing is, you can see this is disable or enable instruction fetches from all pages reachable for this. What this means is, for example, you can disable the instruction fetches from your stack such that stack overflow, buffer overflow, basically attacks can be eliminated from this. So what about the fourth level? The fourth level is the last one. You can see it's again the same thing, okay? And except that now what I have here is this one, okay? This is the physical page address. This is the one that's being different, which is again the physical page number. And along with this, we also have this dirty bit, okay, which is if we have written anything in that, then that's basically updated here. You see. Okay. So I didn't have the dirty bit in the previous one. Now in this case, I have here.
Hocam, a small interruption.
Mm-hmm.
This part is from our computer organization book, right?
Mm-hmm. Yes.
Yeah, so if anyone wants more details, they can check out the virtual memory chapter of the book.
No, well, these slides, this is the second pass. I have already covered them in more detail in computer organizations. But anyway, I could have passed easily. Okay, so this is how it works. We have VPN1, okay, and CRT. This is the beginning of this, and you can see that from the level 1. And now in this case, note that at the end of this whole thing, you will get your physical page address here. PPN is 40 bits, and then by adding it with page host, you'll get your physical address. Okay, and in here, that is the nice thing. Like how many entries do I have? I will have 2 to the power 9 page table entries here, right? And each entry would tell me about 512 gigabytes per entry. Okay, when you go down to here, each entry will point to a 4 kilobyte region. Okay, so you can see that if I have a null here, okay, because imagine this whole region between your heap and the stack or other things, you will have a null here will create a 512 gigabytes of null region. Okay, and you can then fine tune this. So a lot of the L2, L3, and L4 level page tables do not exist in reality. Okay, despite the fact that it's working as such. Okay. And this is the last thing that I will stop. I will discuss and then stop. So in the case of a Linux process, this is a more detailed versions of the cartoon that I've been using from the beginning of this. So in here, I will have some unused space, and that's why you have this null pointer access is accessing here, and it's not accessible. That's why you get segmentation fault. Okay. Then you have your program text code, initialized data, uninitialized data, which is again and then malloc. Then here's a memory map region for shared libraries, user stack. And this portion is, for example, this is, you can do this by just updating it in your page table for that process. Okay, then you can say that this is my kernel virtual memory, and there can be there's certain data like process specific, like this is operating system resources. Okay, the page tables, etc., they are all here. And this is specific for each process, okay? And then there's other portion, like the kernel code. For example, when you do a system call, when there is a code, right? It's like a function call. That code actually appears in this portion, and this is identical for each of the process, okay? Because it's shared. So you can see basically how this whole thing basically works up with the virtual memory system. So let me stop here, and if you have questions, I can take them. Otherwise, basically, I think we'll be. I will try to speed up a bit, just to remind you that since last week due to May 19th celebrations, we missed 2 hours. That caused a little bit synchronization, but today I have passed a little bit, so you're ahead of the other section. So I think that if we speed up like this, we will be covering that extra 2 hours, and hopefully it won't make much of a difference.